Parts for projects. What do we have today? Well, we have some resistances. So, what kind of resistances? What? Those are chips. I was expecting a resistor assortment. So there's two sets of 10 ICs, 74HC165, CMOS 4094. Kind of hard to see, lots of glare. 10 pieces CD 4094, DIP 16, 8-stage shift and store bus register. $1.26 from Orchid. I'm not even going to scroll down and look for a description. They never describe these things, but I do. So it's an 8-stage shift register with serial in, parallel out. There's an output available to cascade a number of these devices on QS, so you can string a bunch of these together, get more than 8 bits. So you would have data in and then QS out to data in, cascading and expanding the system. Just some digital logic chips to have in stock. You never know what you might want to do here. 10 pieces, 74HC165, 8-bit parallel load shift registers. $1.64 from Orchid. Not likely to be a description down below, so let's look it up ourselves. I seem to be collecting shift registers, so these are 8-bit parallel in with a serial out shift register. So the concept here would be similar to gamepads like Nintendo and Super Nintendo, even though they use a CMOS 4021 shift register. If you have a bunch of inputs, buttons or sensors, whatever, as long as it's digital data, not analog, you can latch all of this data in and then clock it and shift it all out on one serial output into a microcontroller or something like that. So you could use this sort of like a GPIO expander for digital inputs. Latch in a bunch of data, shift it in serially, as long as you have time to do this shifting between latching in more data. Like if it's a push button or something like that, you'll have lots of time to shift all these 8 bits in before you need to latch in another set of data, because a push button is a relatively slow signal. DB25 adapter. I wonder if that knife is getting a bit blunt. It felt like it. Oh, these are gender changers. So it's a DB25 like the old school computers, old serial ports and parallel printer ports. So it's got a female on each side. If you have a male connector on a cable and you need to go to another male cable or connector on a computer itself, you plug this in between and you can plug a male into a male. Very useful for when I get back into computer experiments and modems and stuff. DB25, female to female, 25-pin mini gender changer adapter cable extender connecto. Each one is $1.39 from Zhawei 2013, and I got 2 of them. If I want 2 modems set up and I end up with cables or connectors where I have 2 male ends, I plug the connector here, and then I end up with female pins on the output, gender changing it. So I figure 2 of these should be enough. IC chip. Well, I see several chips, and it's hard to get at these. Oh, okay. Okay, I'm not going to need to magnify what's on the chip because it says 4049. I think that's a hex inverter, quantity 10. So there's the 10. New 10 pieces CD 4049, hex inverter, DIP 16 IC, $2.35 from E Come On 2013. Not too much to say about a hex inverter. It has 6 inverters in it and some power pins. Very nice to have around though for your digital logic library of parts. And you can make oscillators out of these. You can make simple little synthesizer tone generators. You always need inverters. Radio sensor. Now, that's a bit vague sounding. So what actually is this? Oh, this I've been waiting for so long. RFID sensor and a sample fob and card tag. I must have ordered this last December or January. And I've been waiting for it. I already opened a package of fobs and a package of extra cards. So here's the actual board. All right. So we have a couple of headers. We have a choice of right angle or straight through for the end here. We have a card and a fob. And the sensor, RC522. There's the chip, crystal, miscellaneous stuff with the header, and here's the antenna area. The long-awaited MFRC522 RFID Radiofrequency IC card inducing sensor reader for Arduino M5. All of this, the receiver circuit, and 2 test tags, $1.88 from GC Supermarket. So read and write at 13.56 MHz contactless communication card chip. It's an NXP device. Sounds like there's a whole lot of datasheet copy and pasting going on here. What we need to know really, this is a 3.3 volt device. It'll draw 10 to 26 milliamps between sitting around or actually operating, communicating. Has a sleep current of less than 80 microamps. Supports all these cards. Operating temperature, you know, if you want to use this outside somewhere, you can go down to -20 degrees Celsius. That may be an important spec depending what you're doing, but I don't think I'll be really using it outside. Has an SPI interface and operates up to 10 megabits per second. I look forward to getting this thing going. And apparently I ordered a plastic clip, which oddly looks like LEDs. Looks like there's about 20 in here. They have clear housings. There's no idea. I don't know how long ago I ordered this. I have a suspicion these aren't regular LEDs, mostly because I couldn't get them to light up when I tested them, so they're either maybe infrared transmitters or photodiodes, phototransistors, something. Let's look it up, see if we can find anything in my listing that matches quantity 20 of an LED-looking 5mm package. 20 pieces 5mm, 940 nanometer infrared launch emission tube diode LED lamp emitting. Emitting? I think these are detectors. 20 of these are 99 cents from Z Home 2015. Photodiode, photosensitive diode, light sensitive diode, not emitters. And you know, there's not much that they say about this other than the size of it, and they're being confusing about if it's a detector or emitter, but they do give the clue here. It's 940 nanometer infrared, if we can believe this. So let's try and use some empirical evidence here. If we look up a datasheet for some random photodiode, this is a photodiode, and some idea of specs. For a typical one of this size, you might be able to dissipate 150 milliwatts at room temperature or below. You might be able to handle a 32 volt reverse voltage, which is fine for the workbench. We're not designing a product with this. And the wavelength for peak sensitivity on this receiver is 940 nanometers. If we were to treat this kind of like a general purpose NPN or PNP transistor, and we don't care what the gain exactly is, we just want to know what kind of specs would be realistic. We know that this is our wavelength of light. We're just going to hook this up maybe to op amps, transistors, experiment with it. Something like this is good enough. Typical applications of photodiodes, I'm just going to mostly use it as a kind of an on-off switch, detecting light. Whether I use it to switch something on and off or use it to receive data, which is a bunch of on and off, as opposed to a proportional light meter kind of application. But you can do all kinds of things. There's some sample circuits here. Here's a light meter. So I guess it has this analog meter that it will drive based on how much light you get. Or here's more what I'm thinking, a fiber optic link. Have a receiver over here and an op amp to condition it and try to receive something you're transmitting optically. A smoke detector application, if you have this little chamber and you shine a light in here and you normally get a bunch of light reflected, but you get smoke particles or something else contaminating this little chamber, you're changing the amount of light you're able to detect. so you can trigger an alarm. I don't think I'll be making a CAT scan anytime soon. Pulse monitor for your finger. Shine a light through your finger and detect it. Now that's something I haven't really seen before. Usually, don't they bounce the light off of the same surface they're detecting? Well, maybe this is an interesting idea to try out. All right, some LED-shaped things, some DB25 computer cable gender changers, lots of digital logic, TTL and CMOS, some resistors that don't belong in this mailbag, and my long-awaited RFID tag reader. I can't wait to use this.